Hey guys, if you saw my last video, we built this cool servo gearbox. And before I hook it up to our servo programmer and test it, I was thinking we probably ought to have a quick talk about torque and what is torque. And I'm going to give you an example. I'm going to just suggest that, I was driving my car along, and here's my car. Okay, I'm a math teacher, not an art teacher, so bear with me. And I got a flat tire, okay, flat tire, and I need to change this tire. So I can't find my jack, but I found that there's this big rock right here that I'm going to use as a fulcrum point, and this rock is exactly 1 foot away from my bumper. And what I've done is I found this steel bar, and I'm just going to run it right in there, and I'm going to use this to try to jack up my car. Now here's the question. My car actually, it's not a huge car, but it's going to push down at this point with about 750 pounds of force 1 foot away from our fulcrum, our rock here. So the question is, where does Mr. Rogers have to stand in order to lift that car up? If Mr. Rogers weighs, let's keep the numbers nice and easy here. If Mr. Rogers weighs 250 pounds, okay, where am I going to have to stand? In other words, how far from the fulcrum will I have to be in order to make that car go up? Okay, well, it turns out that if this force is pushing down at 1 foot away from the center of our fulcrum, then it creates what's called a moment, or which is very similar to the concept of torque. And so we would say that this is 750 pounds acting at 1 foot. 750 pounds times 1 foot gives us 750 pound feet. This is a unit of torque, pound feet. And there are other units of torque that we'll talk about. So that's going to have to equal, at the point where it just starts to lift up, it's going to equal my 250 pounds times x feet. And if we divide both sides by 250 here, we're going to find that 3 equals x feet. So I need to be 3 feet from the fulcrum in order to make that go up. So, and if you haven't seen, I've got one of these on my wall in my room, and I think Mr. T has one on his wall. I keep this around because when we're looking at motors in robotics, the manufacturer specifications come in all different sorts of units. So 1 foot-pound, what does that mean? That means that I can lift with a particular motor, if it has a torque of 1 foot-pound, it means at 1 foot away from the center of rotation, I could lift 1 pound, which is equal to 12 inch-pounds, which is equal to 192 ounce-inches, which is equal to 13,826 gram-centimeters, which is the same as 13.826 kilogram centimeters, or 0.13826 kilogram meters, or 0.11299 Newton meters. And you probably won't encounter this one quite as much, but it's good to know in case you have to convert. So if I had 1 foot-pound or 12 inch-pounds, that means I could lift 1 pound 12 inches away from the center of rotation, or I could lift 12 pounds 1 inch away from the center of rotation. So what does this all have to do with motors and robotics and torque? When we look at, let's look at the specs for this motor really quickly. And you're going to see we got some numbers here. We have this stall torque at, I'm going to look right now at 6 volts, because when we hook up the servo programmer, that's what we're going to be running at, 6 volts. So 1.56 pound-feet at 6 volts. That means that at 1 foot away from the center of rotation, this could lift about 1.56 pounds. Now, what's cool about what we did here is that we geared it down so we get more torque. And since the ratio of these teeth on these gears is 3 to 1, we've geared it down 3 to 1. That means we have 3 times as much torque, which means theoretically our stall torque is going to be 3 times 1.56 pound-feet, which is going to give us, what is that, approximately 4.68 pound-feet. Check my math on that. So that's a significant advantage. Now all of a sudden, instead of lifting 1.5 pounds at a foot, you could lift 4.7 pounds at that same distance. So basically what this is doing is, think of it like this. It looks like a wheel, and theoretically it is a wheel, but it's also a lever. That's what's really happening here. So if this motor wants to apply a force, when it turns, it's going to apply a force to that tooth right there on that larger gear. And you can think of it like the car problem. Instead of applying that force 1 unit away from the center of rotation of this gear, it's applying it 3 units away from the center. So it's using this larger gear as a lever. You can think of it as like an infinite lever, and it's going to go around and around and around. It's a lever that you get to keep pushing, and that's where you get that mechanical advantage. So what I want to do in our next video is set up our servo programmer, and let's put some sort of an arm on here with a known weight, and let's go ahead and test and see if we actually can lift 4.68 pounds at a distance of a foot. Because if we can do that, then we can take a look at your design for your robot and your lift and estimate how much you have to lift and see if this guy is actually going to do the job. All right, tune in to my next video, and we're going to hook this thing up and test it. Thanks, guys.